Well, we're talking about compact sets and continuous functions. Let's look at a graphical example here. The following function, this is a question, is or is not continuous and one-to-one on its domain. First of all, let's observe that the domain is correct. The domain I've highlighted in blue here is this closed interval union with this half open, half closed interval right there. So the domain is correct. So the question is f continuous and one-to-one on that domain? And you might think no, because you've thought from the past that a continuous function means you could draw it without lifting your pencil. Well, when the domain is not a compact set, that's not the case. This is a continuous function. If you use the delta, epsilon definition or the limit definitions, this is a continuous function. Even at that endpoint and even at that point. So, it is continuous. Is it one-to-one? It is one-to-one. Can you remember what it means or how you can test it? You can use the horizontal line test. If the horizontal line test fails, then it's not one-to-one. If you can draw a horizontal line that goes through the graph more than once, even right here, well, like my picture may not be perfect, that's supposed to be on the same height as that. So it only crosses it one time. If you're above it, it only crosses it one time here. If you're below that, it only crosses it one time here. So yes, this is continuous and one-to-one. Now, what do we know about this domain? It is clearly bounded, but it's not compact. It's not closed, so it's not compact. So our previous theorem is not going to say much about the inverse being continuous or not. Well, let's take a look at the inverse. I didn't graph it yet because I wanted to remind you a nice, easy way to graph inverse functions. Notice that I sketched with dots anyways the line f of x equals x, the identity function, and I did it here as well. Well, the inverse of an invertible function is simply the mirror image around y equals x. And what that ends up doing is every point, I'll call it xy, on f, means that yx is on f inverse. So what we would get at 1 is something like this. Notice I just flipped that over. What are we going to get here? 2, 2. And this is going to flip over. Let's see, this would go all the way to 1, 3. 1, 3 would be right here. And as we expected, we did not get a continuous function. This function is continuous everywhere in its domain. And what is its domain? The domain of f inverse is everything from 1 to 2 inclusive, the closed interval from 1 to 2. At f of 1 is the value 1, not this value. It is a one-to-one function, obviously. If f is one-to-one, then its inverse will be one-to-one. One-to-one, I think of as being equivalent as invertible. If this is invertible, it's one-to-one. Well, its inverse is also one-to-one and invertible, because this is the inverse of this. Well, anything else interesting here? Is the inverse function f inverse continuous on its domain? No. Obviously. What is the domain? Well, I've already represented that as well. The domain is the closed interval from 0 to 2. Is it, meaning the domain, is the domain of f inverse compact? Indeed it is. It's a closed bounded interval. Let's see what we can say about that. It is, well, it's not continuous, but it is one-to-one. And it's on a compact set. it turns out, by going in reverse, that the inverse of this function puts us right back up here to a continuous one-to-one function. This one, though, is one-to-one but not continuous. So just a couple of interesting examples here. That's actually one example, taking f and its inverse. The domain is compact. If this were continuous, the previous theorem would have applied, but it's not. So anyways, this was kind of more maybe just of a review of what it means for a function to have an inverse.